Hi and welcome to part 3. In this lecture we're going to talk about the canonical and the standard forms. So first of all, just a bit of an overview of the canonical forms. We're going to have a look at what is the canonical form, the ideas of minterms and maxterms, look at the need for using the index when we're representing the minterms and the maxterms. We're going to look at the SOM, which is the sum of minterm representations, and the POM, the product of maxterm representations. So that is sum of minterms and product of maxterms. We're also going to look at the representations of the complements of functions and conversions between these different types of representations. So first of all, thinking about the canonical form, you find that it's quite a useful form when we're specifying Boolean functions because it allows us to do comparisons for equality. It also directly corresponds to the truth tables, which makes it quite useful. And the canonical forms that are in common usage, as I said before, are the sum of minterms and the product of maxterms, the SOM and POM. Minterms are the AND terms, such that every variable is present in either its true or its complemented form, complemented being the bar over the top. Since each of the binary variables can appear either in the normal or complemented form, therefore there's 2 to the n, where n is the number of variables. Given that each binary variable may appear as either the normal or the complemented form, here I've written x or not x, then there are 2 to the n minterms, where there's n variables. Think about this example. How many minterm combinations can we get from 2 variables, for example, x and y? Remember that they're the AND terms. So we have x and y, that is where they're both normal, x and not y, where x is normal and y is complemented, not x and y, where x is complemented and y is normal, and x and y both complemented, so that is not x and not y. We have 2 to the 2 equaling 4 minterms. So maxterms are the OR terms, that is, they have a plus symbol in between them, with every variable present, and either in the true, that is the normal, or the complemented form. In the same way, given that each binary variable may appear in the normal or complemented forms, there's once again 2 to the n maxterms for n variables. Another example, this time for the maxterm combinations given the 2 variables x and y. So that is, we have x or y, where they're both normal, x or not y, where x is normal, y is complemented, not x or y, where x is complemented and y is normal, and finally not x or not y, where they're both complemented. So once again we have 2 to the 2 for maxterms. So here's a table that shows both the minterms and the maxterms, and it's important also to look at the index there. We have to actually keep track of that. We'll understand the importance of that a little bit later on, but for now we can see that index 0 being where the minterm, they're both complemented, so not x and not y, whereas the maxterms are both normal, uncomplemented, x or y. And then the in-between cases where one of the variables is complemented and the other isn't. And notice how it's the opposite. So the x1 is complemented in index 1, y is complemented in index 1 for the maxterm, and then vice versa for index 2. And finally for the third index, for the minterm we have x and y, whereas for the maxterm we have not x or not y. So both minterms and maxterms can be designated with a subscript, and that subscript is already understood to be the standard order which they would fall in. This subscript number corresponds to the binary pattern, and the bits in the pattern represent the complemented or the normal state of each variable listed in this standard order. So all variables will be present in both minterms or maxterms, and they are listed in the same order, which is usually alphabetical. So if we're using ABC, then we list A first, then B, then C. If we're using X, Y, Z, then once again in the standard alphabetical order. For the variables A, B, and C, we can look at 2 maxterms. Not all of the maxterms, but these are 2 examples of maxterms, and that is A or B or not C. For the second one, A or B or C. Whereas these terms are not maxterms because they're not in the standard order. So B or A or C, then A obviously should be on this side, even though this first one is the same. If it was rearranged as this final maxterm, it's not called a maxterm. And A and not C and B, and then the third example. So these are all not in the standard order. And then here's a few examples of some minterms: A, not B, and C, A, B, C, or not A, not B, and C, whereas these other ones are just terms because they do not contain all the variables. Despite being somewhat in alphabetical order, they need to have a B in it. This one needs to have an A in it, so these are all not examples of minterms. So as I mentioned briefly before, the index is important when we're talking about minterms and maxterms. If the index is expressed as a binary number, so that is not as a decimal number like we listed in the table before, but as a binary number, then it can be used to determine whether the variable shown is in its true or its complemented form. So for minterms, if there's a 1 in the index, the binary value of the index, then it means that the variable is not complemented. If there's a 0, it means it is complemented. For maxterms, it's the opposite way around. A 0 means that it's not complemented, and a 1 would mean that it is complemented. And in case that terminology is confusing, you can think of not complemented to mean ordinary, normal. So you could think about this and this one as being just normal. So let's look at an example to make this a bit clearer. So assume that we've got some variables x, y, and z, and the standard order is of course x, y, and then z. Then the index 0, which is in base 10, is the same as 0, 0, 0. The reason why we use all three here is so that we'll have one for each of the x, y, and z, the three variables. And then since we said before that in the case where it's 0 for minterms, then they are all complemented. So we have not x, not y, not z. Whilst for the maxterms, none of them, no variables are complemented for the maxterm. That is, they're just normal. There's no overbar on these x, y, and z's. So the minterm 0, the minterm 0 being a base 10 in binary is 0, 0, 0. Therefore, all of them have got to be complemented, so x not, y not, z not. The maxterm 0, once again, 0, 0, 0 if that was in binary, and we call that capital M with the subscript 0, is the same as x not complemented, or y not complemented, or z not complemented. So minterm 6 is the same as 4 plus 2 plus 0. This 6 is in base 10. Then this would be the same as what that binary number is. Then we say the first one, x, is not complemented, it's normal. The second one, y, also not complemented, just normal. And the third one, z. Okay, this one is complemented, and so we've got an overbar over the top. So now let's think about the maxterm for 6. So once again, let's just write out 1, 1, 0, base 2. And for maxterms, remember that 1 means that it is complemented. So we have not x, then the next one is also 1, so or not y, and the third one is 0, and if it's 0, it's not complemented, or z with no overbar. So that's good, got the right answer. So let's look at a few more examples here. In this table, although not every index is shown, we're skipping out a few, gives you a good overview. You should be able to sense a pattern here, and the pattern should match what I explained in previous slides. So where index is 0 and we have 4 variables, then the binary pattern is 0, 0, 0, 0. Minterms, all of them are complemented. Maxterms, none of them are complemented. Okay, the other extreme being 15, where the binary pattern is 1, 1, 1, 1. The minterm, none of them are complemented. There's no overbars on any of them. The maxterms, all of them are complemented. So let's think about index 1, 0, 0, 0, 1. Minterm, A, B, C are all complemented, D is not complemented. So for the maxterm, we should have A, B, and C not being complemented and D being complemented. A or B or C or not D. For this one, 0 means complemented, so not A, not B, C and D not complemented. For 7, we've got 0, 1, 1, 1. Remember, 0 means complemented, so not A. 1 means not complemented, just normal. So B, C, and D are all not complemented. 13, we have 1, 1, 0, 1, being the binary pattern for 13. 1 means that it is complemented, so we have A, B, and D all being complemented, C not being complemented. So let's write that out. A, or not B, or C, or not D. Okay, that's right. So the minterms and the maxterms actually have quite an interesting relationship. And let's quickly think about the De Morgan's theorem that was presented in the first week. so that is where we have x and y all complemented, then it's the same as not x or not y. And notice how the overbar in the first one goes across both of the variables and the and symbol, whereas in the second it only goes across the individual literals. And De Morgan's theorem says that x or y, or complemented, is the same as x complemented and y complemented. And so let's think about the simple case where it's just two variables. We've got x and y, and we had the minterms. In this case, we've got Maxterm with index 2, and we've got Minterm here with index 2. Maxterm index 2 is not x or y, and Minterm with index 2 is x and not y. And actually, capital M2, Maxterm 2, is the complement of Minterm 2, and vice versa. So that is to say, M2 is equal to complement of little m2, and also little m2 is equal to the complement of big M2. And it is known that De Morgan's theorem holds for n variables. So no matter how many variables there are, we only had 2 in the first case, but even if there was n variables, it still holds true. So we can say that the maxterm I is equal to the complement of the minterm I, and the minterm I is equal to the complement of the maxterm I. So let's have a look at the two tables next to each other, one of the minterms with 2 variables and the other of the maxterms with 2 variables. So this is for all the different values of x and y, and notice that the x and the y is the same order. And so this relationship of De Morgan's theorem between the minterms and the maxterms can be seen from the left to the right. You can see everywhere that there is a 1 on the left-hand side of the left-hand table in the minterms table, then there's a 0 in the maxterms table. So 1 is the complement of the other. So something else you might notice from the table is that in terms of the minterm table, there is only one 1 present in the 2 to n terms. That is, for any 1, there is only one 1. Whereas for the maxterms, for any 1, there is only one 0, and the others are 1. So we can implement any function by ORing the minterms corresponding to the 1 entries in the table. These are called the minterms of the function. And we can implement any function by ANDing the maxterms corresponding to the 0 entries in the function table. And these are called the maxterms of the function. So this gives us 2 canonical forms, known as the sum of minterms, SOM, that is because we've got ORs in between, plus symbols in between, and the product of maxterms, that is because we've got dots in between, so it's like their product. Okay, let's try a minterm function example this time, and this example is function 1 equaling to the minterm 1, the minterm index 4, and the minterm index 7. The first step is to write out these indexes in binary, 1 as 0, 0, 1, 4 as 1, 0, 0, and 7 as 1, 1, 1. So since it's minterms, then we know that every time there's a 0, then we're going to write complemented, we're going to write not, and every time there's a 1, we're going to write normal. So let's write this out. Function 1 also equals to not x and not y and z, or x, not y, not z, or x, y, z. Okay, that's good. So we got the first part of the answer right. And now let's fill in this table. We want to be writing 1s where the minterm 1 is true, and 1 where the minterm 4 is true, and the 1 where the minterm 7 is true. And then since this is an OR expression, then the function 1 will be true when any one of these is also true. Let's look at the minterm 1 first of all. So we have when it's not x, not y, and z. And we also see that this is minterm 4, corresponds to index 4. And minterm 7, well, we can see this is down the bottom. Minterm 7 when they're all true. And then, of course, since this is an OR expression, then this is true if any one of these is true. So it's true here, true here, true here, and then false everywhere else. And that's good. Got the answer right. So let's do another example, but this time we've got 5 variables, A to E. And so let's write these indices into 5-digit binary numbers. Remember that since this is a minterm example, when we have 0s, then this is complemented. And where we have 1s, then it's normal. Let's just write out all the variables first 4 times. Okay, so now we're going to put the overbars on the terms that we need to. So we're going to put it on the A, B, C, and the E for the first minterm. And then for this second minterm, which is minterm 9, we're going to put it on the A, the C, the D, And then for the 17th, we're going to put it on the B, C, and D. And then for the 23rd, we're just going to put it on the B. Okay, so great. We got the right answer there. And now let's look at a Maxterm function example. And in this case, we've got function 1 equaling to the Maxterm index 0 and Maxterm index 2, Maxterm 3, Maxterm 5, and Maxterm 6. So once again, let's go through and write out these values in binary. So we only need to have 3 variables. And then we can write function 1 equaling to, and remember in this case, zeros mean normal and any ones mean complemented. X plus y plus z times by the second one where x is normal, y is complemented, z is normal, and then fast forwarding. So that's good, we got the answer right. And now let's fill in the table. Let's just go straight for the indexes. So we have Maxterm 0, and remembering this is where the 0 or the false value is, and all the other values are going to be true. And then for Maxterm 2, so index 2 is false here in index 2 and true everywhere else. And then Maxterm 3, index 3 is false here, true everywhere else. Maxterm 5, false here, true everywhere else. Maxterm 6, false here, and true everywhere else. Since these are all joined by AND symbols, then it's only going to be true where they're all ones. So that is on this line, that is on this line, and that is on the final line. Really just any ones that are non-indexed here. So that would be index 1, index 4, index 7, and then false for everything else. Check our answers. Seems pretty good. Matches up. Yep, that's good. So now let's have a look at the canonical sum of minterms. And any Boolean function can be expressed as a sum of minterms. And for the function table, the minterms that are used are the ones that correspond to the ones in that table. So for the expressions, first of all, we have to expand all terms to explicitly list the minterms. And we do this by ANDing any term that's missing any variable that we need with that variable ORed with the complement of that variable. Let me explain that further by using an example. Here we have a function equaling to x or not x and not y. But notice here that we don't have a y with this term, so it's not a minterm. We need to bring a y into this. In order to do that, we AND that, as in we AND it, with y or the complement of y, not y. And then we expand that out so that we have x and y, or x and not y, or not x and not y. And then we know from that which minterms we're using, because these ones are equivalent to minterm 3, where 3 is equal to 1, 1, 2 is equal to 1, 0, 0 is equal to 0, 0. So let's have a look at another sum of minterms example. And this one's slightly more complicated because in this case, even though we have 3 variables, a, b, and c, the first term is missing the b and the c, and the second is missing the a. So we have to include that in there in this way. So written more cleanly, it looks like this. And then we expand that out completely so that we get these 6 terms. Then we remove the one duplicate term, which is the A, not B, and C, and express them as a sum of minterms. The 7th minterm, we have the 6th minterm, we have the 5th minterm, we have the 4th minterm, and we have the 1st minterm. We need to write it in the correct order, and that is from 1 through to the highest. It looks like this: minterm 1, 4, 5, 6, and 7. So there's another shorthand version of the sum of minterms, which is easier to write, and you will often see it like this going forwards. So in the previous example where we had f equaling to a or not b and c, and we ended up with this expression, then we could also denote this in this shorthand, which is using this summation sigma sign with a little m down subscript here, and then we just simply list the indices. So we list 1, 4, 5, 6, and 7 in this way. And then we can say that the sum of minterms of this particular function of a, b, and c is written like this. So really this is bringing the m that expresses the minterm, the little m, down here, and writing the indices in order. In the canonical product of Maxterms, the POM, once again, any Boolean function can be expressed as a product of Maxterms. From that function table, we have the Maxterms being used corresponding to all the zeros, rather than in the sum of minterms it was corresponding to all the ones. And once again, we need to make sure that we expand it out so that each literal is actually explicitly listed. And we do this using the second distributive law, where we ORing all the terms with whatever that missing variable is, for example, v, with the term equaling to v and not v. And so remembering that v and not v is equal to 0, so we're happy to introduce that. So now let's look at a simple example. We've got a function of x, y, and z equaling to x or not x and not y. And we can notice also that there is no z in either of these terms, so we're going to need to introduce this somehow. And also we're looking for a product of max terms, so we're looking for the individual letters looking something like x or y or z multiplied by x or y or z. This sort of thing with, we don't know where these are going to be, but something looking like that. So first of all, let's apply the distributive law, remembering that some variable or two other variables combined can be also rewritten in this way: x or not x and x or not y. And we know that x or not x is the same as 1, but we can just put a 1 there and we leave the x or not y. We end up with x or not y. Now our problem is to introduce z into the mix, so we can simply do an or with z and not z, because we have some variable and not itself is equal to 0, so this doesn't change the answer of the function in any way. And then we run the distributive law again. We can break this up. The function equaling to maxterm 0, 1, 0, maxterm 2, and 0, 1, 1, maxterm 3. And so that's the correct answer, which is good. So now we'll do another product of Maxterms example. And the idea is to convert this particular function to a product of Maxterms. Straight away we can notice that we're missing, for example, B here and A here and C here. So we need a way to introduce those. So something tricky that we can do is we can think about grouping it like this, calling this X, calling this Y, and calling this Z, so that we can use the fact that x plus yz is equal to x plus y, x plus z. So show that here, x plus yz is the same as x plus y multiplied by x plus z. And this allows us to show this same function in a slightly different form here. And it's starting to look closer to what we expect with a product of max terms. However, we still have these groups that we need to get rid of. These guys can go together, this a not c and this not a, because x plus not xy is the same as xy. So then if we have not a or a and not c, it's the same as not a or not c. And the same with this particular group here, not B or B and C. And so after doing these, we end up with this expression. But notice that we still have this one, this B and C and A and not C. So we need to do this again. You can notice this grouping here and this grouping here. So we're going to turn the not C or B and C into not C or B, and this one into C or A. When we run it the second time, then we get this. So now they're all single literals, and this is the form of product of max terms that we want. Once we rearrange this into the standard order of ABC, it looks like this. And remembering for product of max terms, this corresponds to a 1, a 0, 1, 0, 1, 0, which is, this number is 5, and this number is 2. So we did mention before that the functions are complements of each other. We can have the complement of a function expressed as the sum of the minterms, and we construct this by selecting the minterms that are missing from the sum of minterms. So I did mention that before as well, just look for the in-between ones that are missing in these indices in the canonical form. Alternatively, the complement of the function expressed by the sum of the minterms is simply the product of the max terms with the same indices. So notice here in this example, we've got the indices that were missing from this first sum of minterms, the 0, the 2, the 4, and the 6, and the complement of f is equal to that. And equally, we can say that the complement of f is equal to the product. This is product symbol. Instead of the sigma, we use this symbol to mean the product of the first, third, fifth, and seventh, which is the same indices as in the sum of the minterms. The product of the max terms is the same indices. So the basic steps to convert between the sum of the minterms and product of max terms, or back and forwards, is to find the function complement by swapping the terms in the list with the terms that are not in the list. Let's change from products to sum. So for example, this function, if the sum of the minterms is first, third, fifth, and seventh minterms, Then we form the complement. We have the sum of the minterms with the indices that are missing from the list, and then use the other form with the same indices that forms the complement again, giving the other form of the original function. In the standard sum of products form, the equations are written as an OR of AND terms. In the standard product of sums form, the equations are written as AND of OR terms. An example of the sum of products is like this, where we have all of these being AND terms, and this is individual, and the OR is in between. The product of sums is we have sums, as in we have ORs, and then we have ANDs in between these. There are other mixed forms which are neither sum of products or product of sums. For example, these ones where we have there's an AND term in here, and there's an AND term in here, so making these neither of those SOPs or POSs. So for the standard sum of products, the sum of the minterms forms the end variables, and they can be written directly into a truth table, which can be pretty useful. The implementation of this form is a two-level network of gates, where the first level consists of n-input AND gates, and the second level is the single OR gate, just one OR gate, with fewer than 2 to the n inputs. And this form can actually often be simplified so that the corresponding circuit is simpler. So let's do a simplification example for f equaling the minterms, the sum of the minterms for indices 1, 4, 5, 6, 7. So we write these minterms out, this being 1st, 4th, 5th, 6th, and 7th. We can notice here that we've got an a in front of all of these terms. So we'll simplify this by taking the a out. So all of this simplifies down to 1 with a outside, and then this is the same as a plus not bc, in the same way x plus not x, y equals to x plus y. So now we've gone from what was originally 15 terms all the way down to 3, and that's the same answer that we got. And so when we look at these two pictures, it's quite obvious which one's simpler. The first one where we had the two levels, first being AND and then OR, obviously 15 inputs there. This one only has 3, but the function output is the same. So in the previous example, we actually saw that the canonical forms, that is the sum of the minterms or the product of the maxterms, or other standard forms like the sum of products or product of sums, differ in complexity. And we can use Boolean algebra to manipulate these equations to make them simpler. And the simpler equations often lead to simpler two-level implementations. But I suppose the question is, how can we attain the simplest expression? And is there only one minimum circuit cost? In the next part of this lecture on circuit optimization, we'll deal with these issues. So look forward to it.